Good afternoon and welcome to this interview with Martin Peryea of Jaunt Air Mobility. Our moderator today is Dave Clarke from Aerocar Journal. And Martin is the CTO of Jaunt Air Mobility. And with that, I will go ahead and turn it over to Martin to begin. Go ahead, Martin.
Thank you, Jim. I appreciate it. And I want to thank the Vertical Flight Society and Mike Hirschberg and Jim Sherman for organizing this opportunity for Jaunt to share some information with you folks this afternoon. Again, my name is Martin Peryea. I am the Chief Technology Officer for Jaunt Air Mobility. I have about 38 years of experience in the aerospace business. About 35 years in rotorcraft and about 3 years in fixed wing, primarily aircraft design, development, and certification activities. Okay, I'm going to go through a couple of these charts pretty quickly. I believe everyone is certainly aware of the need to address the issues associated with urban traffic congestion. And if you look at the projected rate growth of automobiles and freight transport, it's going to grow pretty significantly here. There was approximately 100 million vehicles, I think, produced last year, and what's being planned for the next couple of years. Pretty significant number of automobiles, and unfortunately, the infrastructure to support these automobiles is not growing at that kind of pace. If you look at the lost productivity here in the U.S. alone, it's about $160 billion as a result of people, obviously sitting in traffic and not getting to where they need to be. A kind of a shocking statistic here that I, uncovered there a couple of years ago when we were looking at this is that the number of fatalities on the road worldwide. It's pretty significant, and certainly something needs to be done to address, this issue with urban traffic congestion. So, the big question is, what infrastructure is going to solve this problem? There was a study that was done by the University of Berkeley, looking at alternative forms of, transportation in terms of how to address this issue. And one of their conclusions, was the urban air mobility. They felt, high-speed rail systems really doesn't address the issue of moving people around because of the limited number of stops along the rail system itself, and the number of people, quote, that would have to drive to these particular stations would not alleviate that particular issue. They had done a study in the Bay Area which shows that, these particular type of aircraft that we're going to be talking about here, certainly with the aircraft that we're going to be developing, can be used to alleviate that issue with ground traffic. Along comes Uber and their vision of really addressing this problem. Obviously, they have a lot of insight because of their ground transportation business relative to the number of folks that are riding in their cars, where they're picking people up, where they're dropping them off, where they're going, and where they're sitting in traffic. And so they kicked off a program internally at Uber Elevate to really study and potentially address this issue that we have here. They're in a unique position because of the amount of data they can collect relative to this whole ecosystem and the needs and where to put vertiports and the number of aircraft that will be required to serve those vertiports. There's been a few studies done, relative to urban air mobility. You probably have seen some of these studies. And basically the conclusion is that there's going to be a significant number of aircraft that are going to be required to serve this entire new ecosystem. And there is a broad range that's being projected and predicted for the number of aircraft as a function of time. But even the lower numbers that have been presented are pretty significant. And one of the topics I'm going to talk about today is how do you produce the number of aircraft cost effectively to serve this emerging ecosystem of urban air mobility. We believe we have a solution to obviously help address this issue. It is a fully electric aircraft. It has some unique capabilities that I'll talk about here in a bit. And this is a basic, simple, takeaway slide here. The aircraft, does have the ability to take off and land vertically, very similar to a helicopter. We believe it's one of the quietest configurations that are being proposed because of the low disk loading and the low rotor tip speeds, and the fact that it does not have a conventional tail rotor. We believe it also has some inherent safety features upon a total, electrical power loss relative to the driven systems, the motors themselves, because of the high energy rotor system that we have on this aircraft. And it also has some unique features relative to ride quality. And I'll talk about that here in a slide here. And we believe it brings a pretty good price performance value to the customer. I'm going to switch over and play this video here. And while it plays, I'll talk a little bit about the capability of the flight control laws of the aircraft itself. And let me know if you can see the video that's playing. Can you see that, Jim?
I can see it. This is Dave.
Okay, perfect. So it is a compound helicopter, if you will. It is a full fly-by-wire aircraft. We have full-time, 4-axis stabilization on the aircraft. We've decoupled all of the axes to make, quote, flying the aircraft very, very simple. It does have automatic, bank angle hold capability. It has automatic, flight transition capability for both takeoff and landing capability. It's got a, tactical cueing on the pilot controls to give him that feedback as he navigates from point to point. All right, jumping back to the slide deck here. So these are the basic aircraft features. You may have seen some of the material that we've had before, but it does have this high energy rotor system on the aircraft. We call it the ROSA system. It's the reduced rotor operating speed capability. The rotor is designed, again, for very low disk loading, which helps on both the efficiency of the aircraft in hover and low speed flight. But it also has weights at the tips of the blades that are used for stability and high-speed flight. And that extra weight in the rotor system, adds a lot of stored-up kinetic energy that can be used to help assist the aircraft in auto rotation during the flare aspect of it. We have what we call a zero roll landing capability with the aircraft. It does have redundancy in the actuation systems and the electrical systems. We are looking at certifying an all-weather capable single pilot IFR aircraft. As I mentioned earlier, it does have a full fly-by-wire system, and we are designing to 10 to the -9 capability. One of the unique features that we have in the aircraft is the thermoplastics structural design, which I'll talk about in a following slide here. When you size the propellers for cruise flight, and that power is twice the power that's required for low-speed flight for any torque requirements. And so we actually have redundancy in hover for any torque. Any pair of propellers have full control authority to trim the aircraft in yaw, and also still provide handling qualities at low speeds. It does have a tilting pylon control at the top of the aircraft. The entire rotor system does move fore and aft through a tilting mechanism. And that allows us to do two things. It allows us to have what we call indiscriminate loading in the aircraft. So no matter where people are sitting or how it's loaded up, we can always trim the aircraft towards a level fuselage attitude. And so during takeoff and landing, you don't typically get the pitch down or pitch up motion that you would typically get in a rotorcraft. We are targeting a gross weight of 6,000 pounds for this particular aircraft, and with a cruise speed of 175 miles per hour. So this technology, takes its roots back a decade or so with Carter Aviation. He's done some pioneering work in terms of developing the mechanics, if you will, and going through the necessary flight testing to prove that you can unload the main rotor in flight and slow that rotor down pretty significantly. For those that are familiar with rotorcraft, the advance ratio is greater than 1, which is highly unusual for a typical rotorcraft, which typically operates, in that 0.3 range at high-speed flight. There's been numerous analytical studies done by NASA, Ames over the years relative to, looking at this particular slowed rotor compound aircraft with all positive results. And again, this aircraft has flown over 200 knots, and I believe at an altitude of 12,000 feet to really demonstrate the capability and the stability of the rotor system. So we've effectively taken the best attributes of a fixed-wing airplane and a helicopter, which is the most efficient hovering device. And the wings on this particular aircraft are more like sailplane wings. They don't have a conventional flap because they're not needed or required for takeoff and landing. And so they're relatively high aspect ratio, which improves your flight efficiency of the aircraft itself. And so this fundamentally is the concept of our aircraft. Obviously, as you transition from helicopter flight mode into airplane mode, the lift on the rotor system diminishes while the wing, picks up the flight loads. It becomes wing-borne. And in airplane mode, the aircraft feels and behaves and sounds like an airplane. It's very, very quiet. You really don't hear the rotor system or feel the rotor system. So all of the traditional vibration levels that you would typically get in a rotorcraft at high-speed flight don't exist. Again, at low speed, the aircraft, behaves very, very similar to a helicopter in terms of handling qualities and the control systems that we're putting into the aircraft. It transitions pretty quickly into airplane mode. And then again, it's the same controls that basically control typical, fixed-wing control surfaces. It does have ailerons, a rudder, and an elevator. So this is one of the unique features, one of the safety features, and it's something, the industry really needs to address is what happens when you lose, electrical power to your drive system. And, you know, obviously you're going to design a system that's going to be very reliable. So that event is going to be relatively low from a risk perspective. But as you all know, you know, things do happen for one reason or another. And, you know, pilots unfortunately still run out of fuel today, and they could easily run out of battery power if they're, quote, not paying attention to, you know, what they're doing. And so depending on the altitude of the aircraft, the landing area, you know, obviously becomes very, very large. And with the amount of stored up energy in a rotor system that we have in this particular aircraft, no matter where we are in the flight path from a design perspective, you can actually land the aircraft with 0 forward speed and basically 0 rate of descent. You can put the aircraft down very, very softly with just the amount of stored up kinetic energy in the rotor system, which is a pretty unique requirement compared to today's traditional rotorcraft. We've done some analysis, you know, relative to the acoustic signature of the aircraft, and I pulled just one representative chart out of a more comprehensive deck. We did solicit the help of an acoustics expert that has certified quite a few rotorcraft, and he has performed this analysis for us in terms of predicting, you know, what the signature level would be at these particular points that are required for rotorcraft certification. This particular chart is the approach noise level. The graphic on the left side of the chart kind of depicts the flight condition for the certification test point. And so we wanted obviously to use the exact, you know, flight conditions because there's published data out there for representative rotorcraft at this particular flight condition. And as you can see with the ROSA configuration with the Jaunt aircraft, we're pretty low relative to obviously, you know, rotorcraft at the same weight levels, and exceeding, you know, Uber's objective, which this particular chart was generated some time ago. So this objective may have changed, but it's in that neighborhood. So certification, we've done a lot of work relative to understanding, you know, what our certification bases, you know, will be for this particular aircraft. If you go back in history a little bit, if you go back and look at the FAA, you know, definitions of various flying aircraft that have been certified at one time or another, this particular aircraft is classified as a gyrodyne, which by definition is a rotorcraft. Helicopter, by definition, is a rotorcraft. So Part 27, Part 29, you know, cover rotorcraft certification. And so we're going to certify under Part 29. As I mentioned, you know, single pilot IFR. And when you look at the differences between a Part 27 aircraft and a Part 29 aircraft for what we're doing, there's practically no difference in the certification bases because we're going to address just about everything in Part 29 with this particular aircraft. As I mentioned, you know, it is a fly-by-wire aircraft. So you will be applying the more rigorous standards that are in Part 29, the 1309 requirements. We will design this aircraft for bird strike capability because it's going to be spending, you know, a lot of time at low altitude, which is not required for Part 27. It is required for Part 29. And also structural design considerations. There are some differences between the two parts. We are going to be taking more of a commercial fixed wing approach relative to structural design considerations, so we can reduce and eliminate the frequency of inspections that you would typically find on a typical, rotorcraft, typical helicopter. But inspection is more aligned with the commercial aviation sector. We do expect to operate in the same airspace as a helicopter under Part 135. And as I mentioned earlier, we are designing to 10⁻⁹ for flight critical systems, which obviously require triplex components for a lot of the aircraft systems. This is a very, very high level depiction of our development certification timeline. We are in the process of, laying out those plans to build our demonstrator. We'll have first flight sometime in 2022. This particular aircraft will be kind of a hybrid design, if you will, fully electric, but it won't contain, all of the systems that you would take into a certification program because of time to develop some of these systems in the timeline that we want to get the demonstrator flying. It'll be primarily used to look at the handling qualities of the aircraft, the basic performance of the aircraft, and the acoustic signature, and get some basic data in terms of tuning up some of the flight control laws that are planned. In parallel, we will be designing, the aircraft for the certification program. We are planning on entering our first aircraft into the development program in 2023 with 4 flight test vehicles. These flight test vehicles will be produced, I think, every 6 months apart. Obviously, with the last aircraft in full conformance for the required certification activity, and then obviously generating certification reports and moving into full rate production. So I mentioned earlier the thermoplastics manufacturing technologies that are currently being developed. We are teamed up with Triumph Aerospace Structures. Triumph has an active program in place right now. They're currently working with some major aerospace OEMs in terms of developing and refining this particular technology. And you cannot build the number of aircraft that are needed for urban air mobility using today's aerospace manufacturing processes. Having, first-hand experience, spending time on the factory floor, producing, both helicopters and fixed-wing airplanes, it can't be done without expensive, tooling costs and a lot of human resources. And so Triumph has some technology that they've been developing. Some of this technology is actually in production in secondary structural components. But we're looking at using, this technology for primary structural components, where large sections are hot press formed to the required shape, and then these sections are welded together, fused together, depending on what terminology you want to use, using an induction heating process, which is the key enabling technology. And we've laid out a pretty detailed manufacturing plan relative to, what this factory of the future would look like to produce the number of aircraft that are required, with minimal touch labor relative to, building the airframe. Obviously, the systems that go in the aircraft will still need to be, manually installed. That's typically not the pacing item when building and assembling aircraft today. So we're pretty excited to be working with Triumph. They have a fairly large engineering team that primarily does structural design for all of the major OEMs. And so that's going to obviously assist quite a bit relative to what we're doing. We do have some additional partners that are on board. We haven't publicly announced some of our key tier 1 suppliers yet relative to the other aircraft systems. There should be hopefully an announcement here coming up in the next month or so relative to some major tier 1s that are taking on a pretty significant portion of the design of the aircraft from a systems perspective, including the battery systems and the flight control computers. Kind of hinted, at this factory of the future. We are working with Dassault. We're using the 3D experience set of tools, 3DX, cloud-based system in which all of our suppliers can work in. So we have a single source of engineering, and where the E-bomb and the M-bomb are one and the same. Like I mentioned earlier, we have laid out a build plan. And if you're coming from an aerospace background, you look at the rates and you kind of scratch your head as how can this be done? You're coming obviously from the automotive industry, they're like, why are you going so slow? And so we really feel that we have a plan, a pretty solid plan to hit these rates. And we are looking at setting up, 2 different production facilities. Certainly the first one here stateside. So that was the last of the prepared slides. I didn't want to take up all of the time, chatting, because I know there's probably a lot of questions that you may have. And so, Jim, I'm going to stop the slide presentation here and take questions at this point.
So I think I'll jump in if that's okay. This is Dave. I've got a few questions, but I will take one that Brian Garrett Glazer asked earlier. When you referred to this aircraft having flown at over 200 knots and an altitude of 12,000 feet, you're referring to the Jaunt aircraft that we're looking at on screen now, your prototype, is that correct?
No, I apologize for that confusion. No, it's the Carter aircraft, the technology demonstrator aircraft that Carter Aviation flew, which was primarily focused on maturing and developing the rotor technology, which is on this aircraft. So obviously a different airframe and a different propulsion system than what we're using, but the rotor and the tilting pylon are the same.
Got it. I apologize, Mr. Alcock, I don't know your first name, but Mr. Alcock asks, what is the main, Charles, thank you, Brian. Charles, what is the main focus of your engineering team's work right now? When will you start building the first demo aircraft?
Yeah, that's a good question. So our focus right now is to really lay out the system definition, system requirements, and getting our key suppliers on board. So we've been going through the process of talking with various tier 1 aerospace suppliers and getting the supplier relationships established and down selecting to the key suppliers. Jaunt is not intending to hire a significant number of engineers. We will hire a moderately sized team of engineers that will be working primarily with our supply base who will be doing, the majority of the design activity. And we've started, that process. Some suppliers have already started that design activity. Triumph, for example, has a team in place that are looking at the preliminary structural design. And we intend to start fabricating, parts towards the tail end of this year.
Very good, thank you. Graham asks, how does the drive system work? And do you power the rotor for takeoff and landing and auto-rotate in forward flight?
Yeah, so it is a hovering aircraft, and so the rotor is powered, obviously in hover and in low-speed flight. There are a pair of electric motors that drive a reduction gearbox that are mounted in the tilting mast, tilting pylon, and obviously for low-speed flight, again, that's really the primary motive driver in low speed. As you transition into high speed, the power requirements, drop pretty quickly on the main rotor. And of course, the propellers are providing all of the propulsive force used for cruise flight.
Thank you. Mike asks if you can explain what your personal involvement has been with regard to the Carter technology and the other major jaunt partners such as Triumph.
Yeah, so there's a long history with myself actually and Carter Aviation back when I was working with Bell Helicopter. Bell had spent some time investigating this particular technology and was working with a sister company of Textron, AAI, who was developing an unmanned system using this particular technology for a Army UAS mission to support, the war over there in the Middle East. And those requirements had changed, and that program was stopped. And so I've been very familiar with the technology as a result of that. And Bell actually had a lot of their tech fellows spend some time, analyzing this particular technology suite.
Thank you. Ken asks, what is the wing area of the aircraft and can it glide?
So it can glide. I don't remember offhand what is the wing area. It does glide like a sailplane, if you will. And so there is a trade-off between carrying wing lift and rotor lift in a auto-rotative state. Obviously in high speed, the wing will be carrying majority of the lift. But as you slow down, as I mentioned earlier, you have the ability to land with zero forward airspeed. At that point, all of the lift is on the rotor system. And so there is a trade-off between the two. And obviously the glide is a function of the lift over drag of the aircraft itself, which we are estimating to be around 12.
Thank you. Nicholas asks, can you tell us about the counter torque of the electric propellers on the wings, and are they wired parallel or series?
Yeah, so you'll notice there is no tail rotor on the aircraft, which is the second largest noise generator, for a conventional helicopter. And so we put, quote, the tail rotor on the wings. And as I mentioned earlier, when you do a sizing exercise for cruise flight, you have twice the power or control authority that you need for low speed and hover anti-torque requirement. So the propellers are hooked up in pairs. There's a redundant electrical system for each of the pairs. And the propellers have both RPM control and pitch control. And so we are able to pitch the propellers into a negative thrust direction. So one side would be thrusting forward and the other side would be thrusting backwards, so that you can generate almost a pure couple or pure torque, which helps relative to not generating a side force or an adverse roll on the aircraft like you would typically get with a conventional tail rotor.
Thank you. Graham asks, what battery technology are you using or assuming will be available, chemistry and energy density?
Yeah, that's again, another really good question. We have selected a key supplier that will be developing and certifying the battery system on the aircraft. They are actually going through that analysis relative to battery chemistry and form factor of the cells. Obviously, certifying for crashworthiness is extremely important to us. We do plan on meeting, Part 27/Part 29 crashworthy requirements, and doing a similar type of drop test as you would with a conventional aircraft with fuel on it. And so that analysis in terms of the optimum chemistry and form factor of the cells is in work. We are using for our analysis, because we use the Uber mission to do the aircraft sizing, which is a battery that is at its end of life, and also with the required reserve energy in the battery system itself, which is roughly 20%. And that equates to 153 watt hours per kilogram.
And what is the charge rate that you're targeting for the battery, Brian asks?
Yeah, so again, kind of driven by, Uber requirements and Uber guidance. The fact that we can fly so efficiently throughout that entire mission, because there is a hover segment on both takeoff and landing, which is pretty demanding for obviously an electric aircraft. And so you do deplete, the battery between missions, and you have the opportunity to recharge your battery for a period of time. And that time is approximately 7 minutes as you load and unload passengers. And there's a requirement that you should be able to continue, that sort of sortie for a 3-hour interval. And we are looking at 166 kilowatts.
Question for me, what is the anticipated range of the aircraft, flight range?
So again, that's a factor depending on your cruise speed, how much gross weight that you have in the aircraft. And again, I go back to, the Uber requirements, which is basically 980 pounds at a 60-mile range. We can exceed that. And again, that's at the higher airspeed of 175 miles per hour. If you drop your airspeed down, you can get a better range. And obviously, if your gross weight is less, you can get a better range. And so you do have a traditional payload range chart for the aircraft.
Okay. Ken and Brian asks, how do you achieve low noise for takeoff and landing with a large rotor?
So there's three elements to rotorcraft noise, actually noise for any fan. The number one driver is the tip speed. That has the most significant bearing on noise, and it's typically a function of the 6 power of the speed of the blade tip. The second factor is the blade loading, which is equivalent to the disc loading. And then the third one is what we call thickness noise, which is basically the thickness of the blade just traveling through the air. So we operate at a relatively very low tip speed, sitting on the ground right before takeoff. It's 600 feet per second, but it drops very quickly as you transition from basically a hovering type flight to forward flight. So the acoustic profile drops, but we also have a very, very low disc loading, lower than any traditional helicopter that's out there today, and that helps pretty significantly with the acoustic signature of the aircraft. So tip speed and disc loading, those are your two big drivers, and not having a tail rotor.
Got it. Nicholas asked how the rotor is powered and the mast tilting system.
Yeah, so there is a pair of electric motors and a gearbox up there that drives the main rotor, and they mount vertically, and they do rotate with the tilting mast, the tilting pylon, and so it's a relatively slow motion. It's more of a trim type device as opposed to something a pilot would control. It's going to be an automated system through the flight control system, but it is electrically driven, and we don't use a conventional helicopter swash plate pitch link system that you would find. We actually are using a tilting hub design. And so you don't have the traditional swash plate or pitch links. We actually tilt the hub itself at the very top. And so the actuation system is all in the same axes as the tilting pylon. And it greatly simplifies the rotor hub design, both from obviously a design perspective, but form factor, and then maintenance. You don't have the traditional rotor controls up there that you have to constantly maintain.
Thank you. Graham asks, what is your funding status, i.e. seed, Series A, some other stage? And Brian suggests that perhaps you're approaching this as a distributed capital investment between yourselves and suppliers. And if that's correct, how does that impact the amount of money you need to raise? So what is your status? And I guess what is the funding model?
Yeah, I'll share a little bit there, not too much detail. We have been self-funded for a period of time. We're actually in the process of kind of closing this what we call a friends and family round right now, and we're working our Series A. Obviously, what's transpired here in the markets in the last few weeks has had a bit of an impact, relative to where we are relative to our plan. Fortunately, the feedback we're getting from the investment community has been positive relative to moving forward with the plans that we had set forth. But you kind of hit the nail on the head relative to our key tier one partners. They are committed. They're very confident in the configuration that we've laid out. They're extremely confident in the team, that we have assembled and, will be assembling. And so they have obviously, stepped up and are contributing, obviously, a significant amount of the costs associated with development.
Thank you. I have a question. What is your target initially and then long-term during production as to how much one of these vehicles will cost to purchase?
I'd rather probably not get into that detail. Obviously I have a lot of experience coming out of the rotorcraft industry, relative to costs. And obviously, a big driver to that is the amount of touch labor associated with building aircraft, which can add up pretty quickly. And so we are going to be extremely competitive, relative to what we think we can produce this aircraft for. It is in line with what Uber is anticipating, relative to what the cost is per unit. And we have, done some modeling, relative to both the return costs and the maintenance costs associated with this particular configuration. We've been doing that modeling for some operators, and it looks pretty attractive, and we're pretty confident relative to our targets.
Thank you. Ken asks, how much more expensive is it to certify this aircraft at FAR 29 versus 27? And will the benefits outweigh the costs?
Yeah, that's a good question. And, having firsthand experience, having gone through a couple of rotorcraft certification programs here recently, there practically, will be no difference really between the two certification programs. When you look at what you have to do for Part 27, you pretty much check nearly all of the boxes associated with Part 29. The biggest differences, as I mentioned earlier, one is, designing for fatigue. There are some differences between 27 and 29. And of course, that drives inspection intervals. And so we're going to design, as a practice to eliminate and reduce inspections. And so we're going to already check that box for Part 29, bird strike. That's another difference between the roles. And again, we're not going to develop an aircraft that doesn't have, bird strike capability. So we've checked that box. The other big area is in the system safety analysis, the 1309 aspects. And the fact that we're having a fly-by-wire aircraft, drives you to the same requirements as Part 29. And so there is no cost difference really between the two.
Thank you. Nicholas asks, where'd that one go? If you have any plans to swap battery packs.
So we have a particular customer segment that we've been talking to that won't have the infrastructure in place to rapidly charge the battery as at what Uber is kind of planning, at some of the vertiports. And they would like the ability to be able to, quote, drop the battery pack, roll it out of the way, roll another system, and, plug it into the aircraft. And that way they can, charge at a much lower rate and operate the aircraft in that manner. Obviously, there's some design challenges associated with that, additional weight and costs, but it is something that we are going to undertake as a trade to understand, what that impact would be for the aircraft. It could be offered as a kit to a variant, but that's something we need to explore as we get into the structural design requirements for the battery system itself.
We're nearing the top of the hour, so just a couple more questions. Jim from VFS says that you presented a schedule somewhat different from what Uber Elevate is planning, i.e. 2020 demo flights and 2023 revenue service. Does that mean you're looking to accelerate your schedule to match Uber's schedule?
No, unfortunately not. Having been through quite a few development programs, I've laid out a success-oriented program. Maybe we got a slight late start, relative to the other Uber partners, but we really don't see how we can accelerate the plan, relative to, what we laid out without, a significant increase in costs associated with executing that plan, and then obviously the risk associated with that.
Great. Two more questions and then we're done. One from Rick. Since you're looking at producing aircraft at a rate closer to that of cars, do you think you have a sufficient market for the aircraft that will have, and you'll be able to find enough pilots for them?
Yeah, that's a good question. It is a new market. You're not selling into the existing market. And so, no one has that crystal ball to really understand how quickly the market will emerge. And obviously, the rates would be adjusted to the market demand. Pilots are going to be a challenge. We are designing this aircraft so it, looks and feels and flies like a helicopter from a piloting perspective. And so a traditional, helicopter pilot can, get into this aircraft and take off and fly. All of the symbology, the avionics systems will look very, very similar. Even the behavior of the aircraft will feel like a conventional rotorcraft. But that is going to be a challenge, and so we are developing a training program right now, having some experience with simulation and flight trainers. We're working that plan right now in terms of the number of trainers that we're going to need to train, a whole new cadre of pilots that are going to be required to fly these aircraft. And that's obviously a industry concern right now.
Excellent. I think our time is up. You've been more than generous. There are a couple of other questions, but I'll let those folks approach you directly offline to this conference. And we, all of us, thank you for sharing your time with us today and the details of Jaunt's vision and progress.
Yes. No, I want to thank the entire group for taking the time and listening to what we had to say and offer today. And we'll be more than glad to answer additional questions if they can be sent through the vertical flight, or and Jim can take care of getting that coordinated through our communications person.
Terrific. Thank you all.